Hello and welcome to our fourth video. My name is Tayyib Abul Yaman. The video is about the family of even linear functions. And to discuss the family of linear even functions, we definitely need the x-axis, where x is the independent variable, and the y-axis, where y is the dependent variable. And we're going to choose a member of this family, which is f of x equal to 1, because f of x equal to 1 is the simplest even linear function, and we can get its characteristics listed easily. The characteristics of f of x equal to 1, not characteristics because of f of x, because f of x is a member of this family, so the characteristic of f of x equal to 1 is the characteristics of every member of this family. So we will go ahead and list the characteristics first, and then we will make some conclusions. The first characteristic is the following. F of x equals to 1, we can model it as input process output by the abstraction x feeding a process. In f is a representative of the process, and the output of the process will be equal to 1. If we look at this particular model, the APO model, and we compare it the model to the modeling of functions in calculus. In calculus, the input will be coming from the domain, and the function will map that input from the domain into an output in the range. So if we compare these two models, the abstraction of the IPO and the calculus model of the function, we will know that x could be any value on the domain, and f the process is equal to f of x, and 1 is the output of f of x, which is range. So the function f of x as an input process output, using the abstraction x as input, where x could be any value, f is the process, and 1 as output, this particular function maps every x in its domain to the value 1, where 1 is in its range. So the next point is we're going to go ahead and define the domain. The domain of f of x equals to 1 is the x-axis. And sure enough, f of x equals to 1 implies that the parameter of the function f comes from the x-axis. So whatever the value of x is, be it a large number or a small number equal to 0, or a large negative number or a small negative number, all of the values, each and every value in the x-axis will be candidate for input to the function, but then the output of the function based on that input is going to be equal to 1, constant. And that's why the line or the graph which represent f of x equal to 1 is parallel to the x-axis, and every point in the x-axis is a point in the graph f of x equal to 1 if we drew a vertical line from the point on the x-axis to meet the line f of x equal to 1. So every point in the x-axis is also a point in the function f of x equal to 1 as far as its x component is concerned. So for that, we say the domain of f of x equal to 1 is the x-axis, which represents the set of all real numbers, because regardless of the number of the value of x taken from the x-axis, positive or negative, where the x-axis represents all the real numbers, then since f of x equal to 1, every point in the x-axis has a matching point in f of x equal to 1 vertically within 1 point or 1 unit distance from the x-axis, because the x-axis is at y equal to 0 and f of x equal to 1 at y equal to 1. So the only difference between the x-axis and f of x equal to 1 is the fact that y-intercept is equal to 0 for the x-axis and y-intercept for f of x equal to 1 is 1. Now that we talked about the domain, and the domain being the set of real numbers, which is symbolically we presented just a few points from the x-axis. And of course, the range is our next characteristic. So the range of f is the number 1, since f of x equal to 1 for every real number x in its domain. Since regardless of the value, positive or negative, regardless of the value, large or small, if it's fed into x, then f of x, if fed into f of x, then the result will be equal to 1. And the result is really this line. So the range is 1. We can go ahead and feed each and every point from the domain that we see to the function f of x, and we will see that its output is going to be equal to 1, regardless of which one we choose. So if we choose, for example, 3 will go as input to f of x, but it will produce a value 1, or it will be mapped to 1. If we change from 3 to 2, the result is the same. If we also change to -3, we get the same result. -3 will be mapped by the function to the value 1 in the range. And every value between inside and every value outside this range, if we send it as input to the function f of x, its output will be equal to 1. And that is basically the third characteristic. Let's take a look at the fourth characteristic. The fourth characteristic is the following. For every x in R, where R is the domain of x, f of minus x equal to 1 and f of plus x equal to 1 imply f of minus x equal to f of plus x. It also implies that f is a symmetric function. The equality f of minus x equal to f of x is a condition people use to check if a function is even or not. If this equality is satisfied for every x in the domain of a function, the function is even. We also talked about f of x equal to 1. We can check if f of x equal to 1 satisfies this condition. If we look into f of x equal to 1 for every value, let's take x equal to 1. So if we put 1 here, we're talking about f of minus 1. Then we go to minus 1 on the f of x equal to 1 graph. Minus 1 is right here. So minus 1 is right here, and this is f of minus 1. F of minus 1 is 1. F of minus 1 is 1. We said f of minus x, where x equal to 1, that means f of minus 1. It's equal to f of x, which is f of 1. So this statement, if we replace x by 1, it says f of minus 1 equal to f of 1. And we know that f of minus 1 is to the right of minus 1. And f of 1 to the right of x equal to 1. So f of minus 1 equal to 1, f of 1 equal to 1. Then we can conclude that f of minus 1 equal to f of 1. F of minus 1, which is the one in the right hand side, equal to f of 1, which is the one on the right hand side over here. So f of minus 1 equal to f of 1. F of minus 1, which is this one, equal to f of 1, which is this one. This is f of 1. This condition is the condition that proves that f of x equal to 1 is an even function. And the fact that it is symmetric because this does not apply only to 1 and minus 1. It applies to 2 and minus 2, 3 and minus 3, and every value in the x-axis. We will talk more about the condition for a function to be even and the condition for a function to be symmetric and the relationship between symmetry and whether or not a function is even. We will talk about them in the next couple of characteristics. The next characteristic is the following. For every x in its domain, which is the x-axis, f of x equals to 1 is a linear function. And we have the general formula for a linear function is f of x equal to mx plus b. Since f of x equal to 1 is a linear function, it must be representable by the general formula for linear functions. And if we compare these two, we will see that the x as a term on the right hand side changes in x will change the value of f of x. But on the left hand side, f of x is constant. Changes in x will not change the right hand side. So for this general formula to apply to f of x equal to 1, m must be equal to 0. If m equals to 0, then the impact of x on f of x will be removed because 0 for m implies that the x will be removed from the equation and the x will no longer impact y. So f of x here will be equal to b and f of x equal to 1. So the second conclusion is that b will be equal to 1. And we know b is a y-intercept for f of x equal to 1. So b equal to 1 and m equal to 0 are our conclusions. And that's why we say over here, for every x in the range, f of x equal to 1, and the general formula of linear functions, f of x equal to mx plus b, imply m equals 0, and the y-intercept for f of x equal to 1 is 1 itself. One more time. 1 is the y-intercept for f of x equal to 1 because 1 equal to b. If f of x equal to 2, then b will be equal to 2. If of x equal to 3, b will be equal to 3. Whatever the value of f of x, that value will be equal to b. And if we look at b, b is a y-intercept. If it is a y-intercept, that means b is a value on the y-axis. Be it positive or negative, it doesn't matter. Let's go ahead and take a look at the next point. The next point states that different values of b represent different y-intercepts. And that's true because f of x equal to 1, b will be equal to 1. F of x equal to 2, b will be equal to 2. F of x equal to million, b will be equal to million. F of x equal to minus 5, b will be equal to minus 5. Whatever value f of x takes in the y-axis, b will take. And for that matter, b can represent any point in the y-axis. So this conclusion is correct. Different values of b represent different y-intercepts and their union equals to the set of real numbers. Because if b can cover the y-axis, then the union of all the b's is equal to the y-axis, and the y-axis equals to the set of real numbers. Let's go to the next point. The next point, for every x in its domain R, which is x-axis, and for every y, which is a value on the y-axis, for every value on the y-axis, if we pick up a point in the xy plane, and that point equal to plus x comma plus y, then that point will reflect on the y-axis as minus x comma plus y. One more time, the point plus x comma plus y will reflect on the y-axis as minus x comma plus y. The difference is the following. The plus x will be transformed into minus x, but the value of y plus y will remain plus y the same, and it is going to be the y-intercept of the function. Let us check f of x equal to 1 against this. We said plus 1 and plus 1, where x is equal to 1 and y equal to 1. And this is represented by 1, 1 over here. We said its reflection around the y-axis will be minus x comma plus y. So if x is equal to 1 and y equal to 1, then its reflection on the y-axis will be minus 1 comma 1. And sure enough, 1 comma 1, if it is an object and we consider the y-axis to be a mirror, then the image of this will be minus 1 comma 1, which proves that f of x equal to 1 also passes this condition. It reflects 1 comma 1 to the point minus 1 comma 1. And sure enough, this is a reflection of 1 comma 1. Its reflection is minus 1 comma 1. And this applies to all the values. It's not just 1 1. It applies to 2 1 3 1 and every value. And that we can also use to prove that f of x is not only even, but we can also prove that it is symmetric. How do we prove that it is symmetric? We know the y-axis splits the x-axis into even halves. To the right of the y-axis is the set of all real numbers that are positive. To the left of the y-axis is the set of all real numbers that are negative. Since we have the same number of negative is equal to the same number of positive, then there is symmetry. So the function is also symmetric. So the last point, let's just summarize it. For every x in the domain and for every y value in the y-axis, the point plus x comma plus y reflects on the y-axis as minus x comma plus y. That means the reflection will transform plus x to minus x, but it will not alter y. So plus y remain plus y on the other hand side. And this condition is very important, as we will see in our summaries. So let's go ahead and get to the summaries. To set the stage for the summaries, first of all, we're going to assume or let the statement 4 represent a transformation step. So if we consider this as a transformation step, which is equivalent to number 7 also. State number 7 is a transformation step. Transformation step, by it we mean reflection on the y-axis. And for that matter, let's go ahead and list our first conclusion. A function is even when every point on its domain is y-axis transformable. A function is even when every point on its domain is y-axis transformable. And we just discussed the fact that if every point in a domain is y-axis transformable, then the function is symmetric. So we're saying over here a function is even when it is symmetric around the y-axis. Now let's go ahead and list the third point. Every even function is symmetric. Every even function is symmetric. Mind you, the first one we said a function is even when every point on its domain is y-axis transformable. That means every point on its domain is symmetric around the y-axis. A function is even when it is symmetric around the y-axis. Over here also we're saying every even function is symmetric. So we're also giving example for that. All the functions satisfying f of minus x equal to f of x. And this is the condition that checks whether or not a function is even. So this condition satisfied, the function is even. If the function is even, then it's transformable around the y-axis. It's transformable around the y-axis. That means the function is symmetric around the y-axis. So we can conclude that every function that's even is symmetric. But can we say every symmetric function is even? And the answer to that is that's not true. And the reason is the following. We're going to state first, every symmetric function is not even. And we give example of a family of functions satisfying this condition, f of minus x equal to minus f of x. If we compare the condition for functions that are even and symmetric, we will see the left-hand side of that condition is the same as the left-hand side of the condition of the functions that are symmetric but not even. Now let's take a look at the right-hand side of the functions that are even and symmetric around the y-axis. We will find the right-hand side f of x, but we find the right-hand side of the functions that are symmetric but not even as the negation of the right-hand side of the functions that are even and symmetric. So this negation negates the fact that functions that satisfy this condition are even. They're not going to be even, simply because the condition for even is the right-hand side must be equal to f of x, but the right-hand side is equal to minus f of x. So the minus negates the even property. So the function is not even. So this is a family of functions that are symmetric but not even. So we can say every even function is symmetric, but not every symmetric function is even. And that's why we said every symmetric function is not even. And this is the family of functions that are symmetric but not even. And one thing that we have to observe over here is the following, which is going to be the subject of our next video. So our next video will be covering the family of odd linear functions as opposed to the family of even linear functions. We'll be discussing the family of odd linear functions. For that family, every x and f of x, where f of x is equal to y, but we can just say every x and f of x in their respective domains satisfy the following: plus x, comma, plus f of x equals to minus x, comma, minus f of x. If the set of functions satisfies this condition, then these functions are symmetric, but they're uneven. They are symmetric, but they're uneven. But we cannot say they are symmetric around the y-axis. If we said they're symmetric around the y-axis, they must be even, because that's the condition for a function to be even. It must be symmetric around the y-axis. So this function need not be symmetric on the y-axis. There is one point that we have to understand, which is the following. A function that's even, symmetric around the y-axis, must have only one transformation, and the transformation should be on the x only, not on the y. So x is transformed to the other side as minus x, but y remains the same. So the transformation is in one part of the function, the x only, not the y. The y will remain the same. But what we see here, the transformation is on both sides, on the x and on f of x, which is equal to y. So both of them are transformed. If both of them are transformed, then these functions cannot be symmetric around the x-axis, and they cannot be symmetric around the y-axis as well. And these functions are actually symmetric around the origin. And this is our next video's subject. Thank you for watching our video. Have a good day.